Imagine you're on a journey to the very edge of what's real. You're floating in the silent, velvet blackness of space. The answer is more profound and more terrifying than you can possibly imagine. It is a journey to a place where the laws of physics are pushed to their absolute breaking point. A place where time itself seems to stop for the rest of the universe, all while your body is stretched into a string of atoms. This is the terrifying physics of a black hole, and below you, a patch of perfect darkness, an absence of everything, a hole in the very fabric of the universe. You've been careful, maintaining a safe orbit, but a single miscalculation has sent you adrift. You've just crossed an invisible line, a boundary from which there is no coming back. So, what happens now? What would you actually see and feel as you fall into a black hole? The ultimate trap. Before we take the plunge, let's clear up a common myth. Black holes aren't cosmic vacuum cleaners. They don't suck things in any more than our sun sucks in the earth. From a safe distance, their gravity is no different from any other object of the same mass. In fact, if you replaced our sun with a black hole of the exact same mass, Earth would just continue orbiting it as it always has. It's the boundary where the gravitational pull becomes so strong that to escape, you'd need to travel faster than the speed of light. And since nothing in the universe can do that, anything that crosses this line is trapped forever. And what you, the unfortunate traveler, actually experience, there's no wall, no signpost, no dramatic moment, because now that we've crossed the point of no return, we're heading for the truly terrifying part. The event horizon isn't a physical barrier. You'd sail right across it without noticing a thing. The only difference is, you are now inside the black hole, with absolutely no way out. Inside the event horizon, all paths, no matter which way you turn, lead to the center. Moving towards the singularity is now as inevitable as moving forward in time. To that distant observer, something bizarre happens. As you approach the event horizon, they would see your clock start to tick slower and slower. That's gravitational time dilation, a core idea in Einstein's theory of relativity. Your image would seem to slow down, stretch, become redder and dimmer, until you appear to freeze right at the edge of the horizon, suspended there for an eternity before fading into nothing, though it would get very, very cold. No, the terror of a black hole lies in its density. Imagine crushing the entire planet Earth down to the size of a peanut. That's the kind of impossible density we're talking about. This incredible mass, squeezed into such a tiny space, creates an extreme gravitational field. Albert Einstein taught us that gravity isn't a force, but a curve in the fabric of space. Massive objects create a dip in this fabric, like a bowling ball on a trampoline. A black hole isn't just a dip, it's a puncture, a point of no return. And as our journey continues, we're approaching that very point. It doesn't look solid. It's a sphere of perfect blackness, a shadow cast across the cosmos. This boundary, this edge of the abyss, is called the event horizon, the edge of forever. The event horizon is probably the most famous part of a black hole. Think of it like a river flowing towards a colossal waterfall. Far upstream, you can easily swim against the current. But as you get closer, the water rushes faster. Eventually, you reach a point where the river is flowing faster than you can possibly swim. No matter how hard you fight, you are going over the edge. The event horizon is that point for spacetime itself. Spacetime is flowing into the black hole faster than even light can travel upstream. But here's where things get truly strange. There's a huge difference between what someone watching from a safe distance sees. But for you, you feel nothing. Time seems to pass completely normally. You don't feel yourself slowing down. If your mind is already bending trying to picture those two different realities, and you want to keep exploring the biggest questions in science, this is a good moment to subscribe. The ultimate torture You've crossed the event horizon, you're doomed. But for a moment, you might feel fine. The moon's gravity pulls a little more strongly on the side of the Earth closest to it, which creates our ocean tides. The forces become so extreme that they overwhelm the bonds holding your body together. You are literally pulled apart, atom by atom, stretched into a long, thin stream of matter just like a strand of spaghetti. At the same time, the forces on your sides would be squeezing you, making that stream of atoms thinner and thinner. Now, imagine that force scaled up to an almost infinite degree. As you fall feet first toward the black hole's center, the gravitational pull on your feet becomes exponentially stronger than the pull on your head. An infinity in an equation usually means your theory is incomplete. Modern work trying to unite gravity with quantum mechanics is exploring what might really be there. Some ideas suggest the singularity isn't a point at all, but maybe a bizarre hyperdense object where quantum effects stop a total collapse. Some researchers even propose that pure gravity, with complex quantum corrections, could form black holes without any singularity at all. But these ideas are still on the frontier of physics, waiting for a new understanding of reality to be proven. That feeling doesn't last. Now, you face a force known by the rather charming name. You already know the principle behind it. It's just tidal forces. But the truth is, they're fundamental to the story of the universe. This enormous gravitational difference starts to stretch you. At first, it's a gentle pull, but it ramps up incredibly quickly. The energy they release as they feed on gas and stars can control star formation across an entire galaxy, sometimes kicking it off, and other times blowing the necessary gas away. The tight link between the size of a galaxy's central bulge and its black hole suggests they grew up together, shaping each other over billions of years. And now, thanks to the Event Horizon telescope, we've seen what these giants look like, capturing images of the shadows they cast. These pictures reveal powerful, spiraling magnetic fields at their edge that can launch enormous jets of material deep into space. The horror of spaghettification really depends on the size of the black hole. The singularity, a point of zero volume and infinite density, where all the matter that has ever fallen inside is crushed down. Here, the curvature of space-time becomes infinite. The laws of physics as we know them completely break down. Our best, most tested theories about how the universe works simply stop making sense here. This is the absolute limit of our knowledge. For a small black hole, just a few times the mass of our sun, the tidal forces are so powerful you'd be torn apart before you even reach the event horizon. But for a supermassive black hole, the kind that's millions or billions of times the mass of the sun, the gravity at the edge is much gentler. In that case, you could cross the event horizon completely unharmed, a silent passenger on a one-way trip, only to be spaghettified deep inside, where no one could ever see it happen. The singularity, whether you are now a stream of particles or, for a few moments, still whole. Your journey has only one possible destination, a place that breaks physics itself. According to general relativity, the singularity is the center of the black hole. For decades, this singularity problem has challenged physicists. The bigger picture. It's easy to think of black holes as isolated monsters, only mattering to whatever gets too close. Pretty much all massive galaxies, including our own Milky Way, have a supermassive black hole at their heart. These giants act as gravitational anchors. Our journey to the center of a black hole takes us from the familiar laws of gravity to a place where space and time dissolve. We see time itself warp and freeze. We witness a body stretched into its basic atoms, and we arrive at a central mystery that science cannot yet solve. Black holes are the ultimate expression of gravity, the most extreme environments the universe has to offer. They aren't just objects of terror, but cosmic laboratories pushing our understanding to its absolute limit, and they leave us with one final, lingering question. General relativity tells us this is a one-way trip to oblivion. But what if the singularity isn't an end? What if this point of infinite density could also be a point of creation? Some speculative theories wonder if it could be a white hole on the other side, giving birth to a new universe. The terrifying fall into darkness might not be an end, but a violent, incomprehensible beginning. And that is a thought perhaps even more unsettling than the fall itself.